Welcome. In this lecture, we will talk about a force versus a field, at least very, very briefly to make a point, and that will lead us to a discussion of Newton's third law, which will then lead us to a discussion of defining systems. Force versus field. Let's pretend that Earth is alone in the universe. Now Earth, because it is a mass, produces what is known as a gravitational field, which has been referenced in previous lectures. And the field strength can be represented, and the vector direction can be represented by G with a subscript of E to denote that this is the gravitational field due to the mass of Earth. Let's say that the moon appears near the Earth, and the field interacts with the mass of the moon. Well, what happens? A force is produced on the moon due to Earth's gravitational field interacting with the mass of the moon. What if we reverse the scenario and say, oh, well, let's look at the moon and pretend that it is alone in the universe for a moment. There is a gravitational field, which we denote by G sub m, produced by the moon. Now let's throw the Earth in there, and we see that the Earth is now within the gravitational field produced by the moon. So what happens? A force is produced on the Earth due to the field produced by the moon. So the gravitational field of the moon is interacting with the mass of the Earth, producing a force on the Earth that pulls the Earth toward the moon. Together, we see that the Earth pulls on the moon, and the moon pulls on the Earth. Now a question may be, how are these forces related? The way I've drawn them here, they look as if they are equal, at least in the length that I've drawn the arrows, but they are opposite in their direction. This is important, and this leads us to a discussion of Newton's third law. Newton's third law states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first, which this is what we saw in the previous slide, where we saw the moon is being pulled on by the Earth and the Earth is being pulled on by the moon. A more mundane example is here, where we have a hammer slamming into a nail. So the hammer applies a downward force to the nail that drives the nail into the wood, let's say. Likewise, the nail applies an upward force to the hammer that stops the hammer from moving. What are some other examples of Newton's third law? Let's take a car, for example, driving along the road. The tire of the car pushes on the road. Newton's third law states there must be an equal and opposite force applied, where the road pushes on the tire. Notice the equal and opposite means that the strength of the force is equal, but the direction is opposite. Take a rocket. The rocket pushes on the gas as it exhausts the gas, and the gas pushes on the rocket, which actually propels the rocket forward. Here we have a man who pulls on a spring, and also a spring that pulls on the man. Finally, we have that Earth pulls on the ball, and the ball pulls on the Earth. And again, I want to emphasize that the strength of the forces is identical. They are opposite in the sense they are pointing in opposite directions. So in this final example, we see that the Earth pulls on the ball with some force. But it's very important to note that the weight of the ball, that force of gravity on the ball, is exactly the same as the force applied on the Earth due to the ball. It may seem counterintuitive, but please take note of that these forces are equal in their strength and simply opposite in the direction they point. Let's take this system as an example, or these two planets. The little planet pulls on the big planet with some force pulling it toward itself. And likewise, the bigger planet pulls on the little planet with a force pulling the little planet toward the bigger planet. Now, what if we distribute the mass differently, but the total mass remains the same? Well, the forces will remain the same, and we'll learn a little bit more about this when we get to chapter 9 and discuss the gravitational force in more detail. But the point here is that the forces are equal in their strength and opposite in direction. Again, we distribute the mass differently. The forces are equal and opposite. Again, the forces are equal and opposite. And again, the forces are equal and opposite. Now, this can lead to a question, which is why we need to define a system. Because the issue that may arise in your mind right now is, well, wouldn't these forces just cancel each other? Wouldn't that mean that nothing would ever move, nothing would ever accelerate? Because if forces are equal and opposite, they should cancel out. 4 minus 4 is 0, 5 minus 5 is 0. If they're just equal but opposite in their direction, why does nothing just give away and cancel? Action-reaction forces, which is what these are called. For every action, there's an equal and opposite reaction. That would be another way of stating Newton's third law. These forces do not cancel each other, and I want to take a moment to explain why. So consider a brick. This brick is on some surface, maybe a table, and something is holding it there. So the gravitational force is pulling this brick into the table. So force from the earth on the brick. Now, the table is applying a support force. It's supporting the brick on the table. If the table was not there, there would be no support force, and this brick would simply fall. So this is the force from the surface on the brick. Now, these two forces are not an action-reaction pair. The brick pulls on the earth just as the earth pulls on the brick. These two in the bottom, are the action-reaction pair. But our system is this brick. So our system is the object or set of objects that we are interested in. And the forces applied to that will put that object possibly into motion. Using Newton's second law, we know that the net force equals the mass of our system multiplied by the acceleration. So what am I getting at here? Well, you'll notice that the force from the earth on the brick, well, that's obviously acting on the brick, so that is our system. Force is acting on the brick, but the force from the brick on earth, that's not acting on the brick. That's acting, as it says, on earth. So action-reaction forces are not acting on the same thing. So that's how you know that they could possibly be an action-reaction force, is because the two forces are not acting on the same object or the same system. So action-reaction forces act on different objects, and therefore they cannot cancel each other out. In summary, we discussed very briefly, just to get to a point, the difference between a force and a field, or rather, I used the field as a talking point to get to Newton's third law, and then we briefly defined what a system is, which again, a system is just the object or set of objects that we are interested in. And when we draw a free body diagram, we apply or we write all the forces on our system using the little arrows as I showed you with the brick, and as you've seen in previous lectures in this course. I'll see you next time.